Namaste everyone. Welcome back to the CET class on the topic atoms. In the last two videos, we have solved some 16 problems on the same topic, and today I will continue from there. Question number 17. Question number 17. If an electron in hydrogen atom jumps from third orbit to the second orbit, it emits a photon of wavelength lambda. We all know that whenever an electron jumps from higher energy level to lower energy level, so this is the different energy levels, the innermost level, for the innermost level the quantum number n is equal to 1, and the next higher level n is equal to 2, and the third orbit n is equal to 3, n is equal to 4. Electron is making its transition from third orbit to the second orbit. Third orbit to the second orbit. So the landing orbit is 2, which says that the series is Balmer series. So n is equal to 3 to n is equal to 2. Whenever an electron jumps from higher energy level to lower energy level, excess energy is emitted in the form of radiation. So the wavelength of the radiation is given as lambda. Lambda is the wavelength of the radiation emitted when an electron jumps from n equal to 3 to n is equal to 2. We know that the wave number 1 by lambda or nu bar is equal to, what is the expression for wave number? 1 by lambda is equal to r into 1 by n1 square minus 1 by n2 square. Here n1 is the landing orbit. Here in this particular example, n1 is equal to 2. n2 is the orbit from where the electron is jumping. So n2 is 3. Alright, 1 by lambda is equal to r. What is r? R is Rydberg constant, and we know the value of r. It is 1.097 into 10 to the power 7 per meter. So 1 by n1 is 2 square minus 1 by n2 is 3 square. So 1 by lambda is equal to r into 1 by 4 minus 1 by 9. On solving, 1 by lambda is equal to r into 1 by 4 minus 1 by 9. 9 minus 4 divided by 36. 1 by lambda is equal to r into 9 minus 4 is 5. So 5 divided by 36. So lambda is equal to 36 divided by 5r. 1 by lambda is 5r divided by 36. Therefore, lambda is equal to 36 divided by 5r, or r is equal to, they are inversely proportional. So, r is equal to 36 divided by 5 lambda. This is the expression for r. R is equal to 36 divided by 5 lambda. This is for case 1. In the second part, when it jumps from fourth orbit to the third orbit. When an electron jumps from third orbit to the second orbit, wavelength of the light emitted is lambda. When the same electron jumps from fourth orbit to the third orbit, from 4 to 3, the corresponding wavelength of the photon will be. What is the wavelength of the photon when an electron jumps from 4 to 3? I will denote this as lambda 1. So R is equal to 36 divided by 5 lambda for the first case. For the second case, 1 by lambda is equal to 1 by lambda is equal to R into 1 by n1 square minus 1 by n2 square. 1 by lambda is equal to R into n1. For the second case, n1 is 3 and n2 is 4. 1 by 3 square minus 1 by 4 square. So 1 by lambda is equal to R into 1 by 9 minus 1 by 16. 1 by lambda is equal to R 16 minus 9 divided by 16 into 9. So 1 by lambda is equal to R into 16 minus 9 is 7 divided by 16 into 9. What is the expression for R? From case 1, R is equal to 36 divided by 5 lambda. I will substitute here. So 1 by lambda is equal to R is 36 divided by 5 lambda into 7 divided by 16 into 9. So 1 by lambda is equal to seven divided by, on solving we get 20. So 1 by lambda is equal to 7 divided by 20 lambda, or this is lambda 1. So lambda 1 is equal to 20 lambda divided by 7. So when an electron jumps from 4th orbit to the 3rd orbit, the corresponding wavelength will be 20 by 7 into lambda. So the correct answer is option C, 20 lambda divided by 7. Next question, question number 18. The moment of momentum for an electron in second orbit of hydrogen atom as per Bohr's model is. According to Bohr's atomic model, we know that he proposed, or the Bohr proposed, 3 postulates. In his first postulate, he stated that electrons revolve in stable orbits, which are called as stationary orbits, without the emission of energy. So that is the first postulate of Bohr. And in the second postulate, the moment of momentum or the angular momentum is also called as moment of momentum. So the moment of momentum of the electron in the stationary orbit, that is L. Moment of momentum is denoted by the symbol L, which is equal to integral multiple of h by 2 pi. The moment of momentum or the angular momentum L is the integral multiple of h by 2 pi, where n is an integer. For the first orbit n is equal to 1, and for the second orbit n is equal to 2, and so on. Here L is the moment of momentum or the angular momentum, h is Planck's constant, which constant, pi is a constant. So L is equal to nh by 2 pi. So this is the second postulate of Bohr. In the question we have the moment of momentum for an electron in second orbit of hydrogen atom. For the second orbit, electron is in the second orbit, that means n is equal to 2. For the first orbit n is equal to 1 and for the second orbit n is equal to 2. So L is equal to, n is 2h divided by 2 pi. 2 cancels, L is equal to h by pi. This is the expression for angular momentum for the electron which is in the second orbit. So L is equal to h by pi. The correct answer is option A, h by pi. Next, question number 19. In the question number 19, we have, if an electron in hydrogen atom jumps from an orbit of level n is equal to 3 to n is equal to 2. So electron is jumping from 3 to 2. The emitted radiation has a frequency. Now we have to find out the frequency of this radiation when an electron jumps from level 3 to 2. What is the expression for frequency of the radiation? Frequency nu is equal to R into C 1 by n1 square minus 1 by n2 square. Nu is equal to R into C 1 by n1 square minus 1 by n2 square. Here also nu is the frequency of the radiation emitted. In this case it is the frequency of the radiation when an electron jumps from level 3 to 2. R is Rydberg constant and we know the value of R, which is 1.097 into 10 to the power 7. C is speed of light, 1 by n1. n1 is the landing orbit, n2 is the orbit from where the electron is jumping. So n2 is 3, n1 is 2. Nu is equal to Rc 1 by n1 square. So 1 by 2 square minus 1 by n2 is 3 square. So nu is equal to Rc 1 by 4 minus 1 by 9. So nu is equal to Rc 9 minus 4 is 5 divided by 9 into 4, 36. So nu is equal to Rc 5 divided by 36, or the frequency of the emitted radiation nu is equal to 5 Rc divided by 36. R and C are the constants. So nu is equal to 5 Rc divided by 36. Correct answer is option D, 5 Rc divided by 36. Next, question number 20. Question number 20. Which electronic transition in Balmer series of hydrogen atom has same frequency as that of n equal to 6 to n equal to 4 transition in helium? So n equal to 6 to n equal to 4 transition in helium. So I will write the energy level diagram. So n equal to 1, 2, 3, 4, etc. Electron is making transition from n equal to 6 to n equal to 4. So n equal to 6 to n equal to 4. This is the transition. In case of helium atom, we know that for helium, atomic number Z is equal to 2. For helium, atomic number is 2. What is the expression for wave number? Nu bar is equal to, for helium, so nu bar He, I will write here He indicates that He is nothing but helium. So for helium, R into 1 by n1 square minus 1 by n2 square. In case of hydrogen atom, atomic number Z is equal to 1. So R into 1 by n1 square minus 1 by n2 square. For helium, I will write here Z square. In case of hydrogen atom, no need to write Z square because Z is equal to 1 square is 1. So R into 1 by n1 square minus 1 by n2 square. For helium, Z is equal to 2. So nu bar for helium is equal to R into Z is 2 square is 4R into 1 by n1 square. n1 is 4, n2 is 6. So 1 by 4 square minus 1 by 6 square. Electron is jumping from 6 to 4. So n1 is 4, n2 is 6. Four R into 1 by 4 square is 16 minus 1 by 36. 6 square is 36. So 4R into, in the numerator, 36 minus 16 divided by 36 into 16. 36 minus 16 divided by 36 into 16 is equal to 4R. What is the value of 36 minus 16? It is 20. 36 minus 16 is 20 divided by 36 into 16. 36 into 16. So 4R. So 4 ones are 4 fours. So 20R divided by 36 into 4. So in case of helium, nu bar is equal to 20 into R divided by 36 into 4. This is for helium. For hydrogen atom, which electronic transition in Balmer series of hydrogen atom has the same frequency as that of helium atom? Now let us see in case of hydrogen atom. For hydrogen atom, Z is equal to 1. So nu bar for hydrogen atom is equal to R only. Z is 1. So R 1 by n1 square minus 1 by n2 square. So Balmer series, for Balmer series always n1 is equal to 2. So I will write n1 as 2. 2 square is 4 minus 1 by n square. Here n2 square. n2 is the orbit from where the electron is jumping, that we have to find out. So n2 square. Nu h is equal to R 1 by 4 minus 1 by n2 square. 1 by 4 minus 1 by n2 square. So nu bar is same. So nu h is equal to nu bar h is equal to nu bar for helium. So R into 1 by 4 minus 1 by n2 square is equal to 20R divided by 36 into 4. Here we can simplify. So R into 1 by 4 minus 1 by n2 square is equal to 5R divided by 36. So R cancels. 5 by 36 is equal to, or 1 by 4 minus 1 by n2 square is equal to 5 by 36, or 5 by 36 is equal to 1 by 4 minus 1 by n2 square. So 1 by n2 square is equal to 1 by n2 square is equal to 1 by 4 minus 5 by 36. 5 by 36. One by n2 square is equal to 1 by 4 minus 5 by 36. So 36 minus 20. 36 minus 20 divided by 36 into 4. So 1 by n2 square is equal to 36 minus 20 is 16. 16 divided by 36 into 4. So 1 by n2 square is equal to 1 by n2 square is equal to 1 by 9, or n2 square is equal to 9. Therefore, n2 is equal to 3. So we can conclude that n is equal to 3 to n is equal to 2 transition in case of hydrogen atom has the same frequency as that of n equal to 6 to n equal to 4 transition in helium atom. So N1 is equal to 2. For Balmer series, N1 is always is equal to 2. So N2 is equal to 3. Electron is jumping from 3 to 2. So the transition from 3 to 2 in case of hydrogen atom has the same frequency as that of N equal to 6 to N equal to 4 transition in helium atom. Therefore, the correct answer is option A, 3 to 2. You just write down once and try to solve it by your own. Next question, question number 21. If V1 is the frequency of the series limit of Lyman series. What do you mean by series limit? For the Lyman series, all the electrons are jumping from excited states to N equal to 1 state. So 2 to 1, 3 to 1, 4 to 1, 5 to 1, infinity to 1. So the first electron which is making transition from 2 to 1 is having less energy. The next one is having more energy compared to the first one. Third one is having more energy, and this is having larger energy. Which is having larger energy? The electron which is jumping from infinity to N equal to 1. So this is the series limit of Lyman series. So this is called as series limit of Lyman series. Therefore, for the series limit of Lyman series, N1 is equal to 1. For Lyman series, N1 is always is equal to 1. So N2 is equal to infinity. N2 is equal to infinity. We call this as series limit or the shortest wavelength. For the shortest wavelength is also N1 is equal to 1, N2 is equal to infinity, or for the series limit of Lyman series, N1 is equal to 1 and N2 is equal to infinity. If V1 is the frequency of the series limit of Lyman series, what is the expression for frequency of the emitted radiation? Nu is equal to R into C 1 by N1 square minus 1 by N2 square. Here frequency is V1. So instead of nu, I will write V1. V1 is equal to R into C 1 by N1 square. For Lyman series, N1 is 1. So 1 square is 1 minus 1 by N2 is infinity. For the series limit of Lyman series, N2 is infinity. So infinity. V1 is equal to frequency of the radiation. V1 is equal to RC 1 by infinity is 0. So 1. So V1 is equal to RC. This is the expression for frequency of the series limit for Lyman series. So V1 is equal to R into C. Further, V2 is the frequency of first line of Lyman series. V2 is the frequency of first line of Lyman series. for the first line of Lyman series. So this is the first line of Lyman series. For the first line, n1 is equal to 1 and n2 is equal to 2. For the first line of Lyman series, n1 is equal to 1 and n2 is equal to 2. For this, frequency is denoted by V2. So V2 is equal to RC 1 by n1 square, 1 square minus n2 square is 2 square, 4. So V2 is equal to RC 1 minus 1 by 4 is 3 by 4. So V2 is equal to 3RC divided by 4. This is the expression for frequency of the first line of Lyman series. For the series limit, frequency is RC. For the first line, V2 is equal to, or the frequency is 3RC divided by 4. And V3 is the frequency of series limit of Balmer series. This is the Balmer series. For the first line of Balmer series, n1 is equal to 2 and n2 is equal to 3. For the second line, n1 is same 2, n2 is 4. Similarly, for the series limit of Balmer series, n1 is equal to 2 and n2 is equal to infinity. So n1 is equal to 2 and n2 is equal to infinity. This is in the case of series limit. So V3 is equal to frequency of the series limit of Balmer series. V3 is equal to RC 1 by n1 square is 2 square minus 1 by, for the series limit n2 is infinity, so 1 by infinity. V3 is equal to RC 1 by 4. V3 is equal to RC divided by 4. So V1 is RC, V2 is 3RC divided by 4, V2 is 3RC by 4, V3 is RC by 4. So V1 minus V2 is V1 minus V2. V1 minus V2 is equal to RC minus 3RC by 4. V1 minus V2 is equal to 4RC minus 3RC divided by 4. So V1 minus V2 is RC by 4. RC by 4 is nothing but the frequency of series limit of Balmer series, which is nothing but V3. Therefore, V1 minus V2 is equal to V3. V3 is the difference between V1 and V2. Therefore, the correct answer is option A. V1 minus V2 is equal to V3. Take down. I will stop here and let us continue in the next class.